All right, let's talk about some properties of sampling distributions of proportions. Okay, so again, this is going to be very similar to the sampling distribution of means, but a little different. So again, assuming that the sampled values are independent and that the sample size is large enough, the sampling distribution p hat, again, p hat is the sample proportion, right? The proportion from our specific sample, not the population proportion p, because we'd have to take a census to get the whole population. This sample proportion is modeled with, again, a normal distribution. And the mean of this normal distribution, so again, you can think of p hat is normally distributed with mean, right? It says the mean of this new distribution is our population proportion p, right? That's population proportion. And standard error, the square root of PQ over N. What was Q? Remember, if P is the probability of something happen or the proportion of things happening, Q is just that it not happening. The proportion that, what proportion is not doing this? If P is the proportion of ones, Q is the proportion of 2 through 6s on a 6-sided die. All right. And that's how we calculate the standard error of this sampling distribution. So it looks a little different than the one for means, different formulas, but the theory and the logic and how it looks is actually very, very similar. And so this normal model, looking at this next thing, for a sampling distribution is a good appropriate approximation if these three conditions hold. Independence. Oh, that was the same as last time. Randomization, that's the same as last time. And this last one is basically sample size. But they manifest a little differently. So assuming independence, the individuals in the sample whose proportions we're finding must be independent of each other. If we sample less than 10% of the population, we can assume they're independent. What does that mean? It means because remember a long time ago, we mentioned something very similar to this. It was actually the same thing, is that if we draw without replacement, which is normally what we do when we sample, we don't want repeated data. We draw without replacement, that's not independent. Okay, but we said that as long as like things are big enough, as long as the population is big enough, sampling without replacement and sampling with replacement are essentially the same thing. So we can approximately independent. All right, and so as long as we're sampling less than 10% of the population for this, then with replacement, without replacement are essentially the same thing, statistically speaking. The next thing is randomization. That's the same. And for our sample size, we're just going to model it. Again, this is a rule of thumb. Some people have a rule of thumb of 5. We're going to say that on average, we should have at least 10 successes and 10 failures. Okay, so the expected number of successes, right, should be at least 10. And the same thing with Q. N times P is the expected number of successes. All right, and that's how we use this. So let's do an example. Suppose that 60% of all college students are either very satisfied or completely satisfied with their online shopping experience. Oh, I thought I was going to talk about online classes. I was going to say, no, I guarantee you 60% are not that satisfied with online classes. Recording this during the pandemic. Anyway, suppose 60% of all college students are satisfied with their online shopping experience. Are you satisfied? How satisfied are you? That is the question. How satisfied are you? That's a question that we're asking people. Very satisfied is an option. Completely satisfied is an option. This is a categorical variable. This is categorical data. This is qualitative data. Okay? We can't take an average here, but we're going to count the proportion. What proportion of these people are answering very satisfied or completely satisfied? That's the distinction between proportions and means, numerical and categorical data. And we're assuming that this right here is our true population proportion. 60% of all college students. All means population. Not just a sample, not just a subset. So we decide to take a nationwide random sample of, ooh, that's a big sample. A big sample size of 2,500 college students and ask, do you agree? Are you similar? Is it reasonable to use a normal model for the sampling distribution of the sample proportion? Well, let's check each one of these. Independence. Well, as long as we're sampling less than 10% of the population, we can assume independence. So is 2,500 less than 10% of all college students? Yeah. I can guarantee you there's more than 25,000 college students. Okay, so we got independence, no problem. Randomization, are we randomly choosing? Yep, right there, random sample. So we're good on this. Success failure condition. I'm going to abbreviate this SF. San Francisco. We should have at least 10 successes and 10 failures. Well, P is 0.6, right? So Q is 1 minus that. It's 0.4. 0.6, P, N times P, right? Has to be at least 10. So what's N times P? It's 0.6 times 2,500. All right, yeah, I don't even need to calculate it out. I know that's at least 10. That's in the thousand. It's over 1,000. All right, and you can do the same thing for 0.4. And you can calculate it all out, but right off the bat, I know that's over 1,000. Definitely over 10. So yeah, it satisfies everything. We can use a normal model. Check. And specifically, we're going to use a normal model with these parameters. The mean of our normal model will be P, our population proportion. The standard error, which is the standard deviation of this model, will be the square root of PQ over N. So find the mean and standard deviation of the proportion of survey respondents who agree. Find the mean and standard deviation of P hat. Excuse me. Again, P hat, we use capital letters for the random variable. The random variable of the sample proportion of this survey is normally distributed. And again, the mean for P hat is this proportion, 60%. The standard deviation for P hat, that's going to be the square root of PQ over N. And we'll have to calculate that. P is 0.6, Q is 0.4, standard deviation is 2,500. Let's type that into a calculator. Be very careful with parentheses when you're doing something like this. All right. So the square root of P times Q divided by N is very small, 0.0098. Hold on, let me get back. 0098. We're asking a lot of people. Remember, the bigger the sample size, the smaller the variability. Okay, so the standard error is going to be smaller. We can also draw this. All right, It didn't ask us to, but real quick, right? This is a normal distribution. This p hat is a normal distribution with mean of 60%. One standard deviation is about 0.01. So add a standard deviation. That means this is about 0.61. Another one is going to be about 0.62. Another one's going to be about 0.63. We could do it in the other direction too. 0.59, 0.58, 0.57. So again, remembering what we know about a normal model, it's very unlikely for something to be outside of 2 standard deviations from the mean. So in this sample, it's very unlikely that more than 62% or less than 58% would agree that they like their online shopping experience. It's probably going to be around 60%. So what's the probability that the sample, let's write this down. What's the probability? Oh, we're using p's twice. Probability that the sample proportion is at least 57%. Well, it's a normal distribution. This probability, at least 57. Oh my goodness. 57% is way over here. At least 57%. That's almost everything. Right? This left tail is half of the region outside 3 standard deviations of the mean, and the empirical rule, 68, 95, 99.7%. I'm not going to sing that stupid song again. Says that about 99.7% are within 3 standard deviations away from the mean, which means about 0.3% are outside 3 standard deviations away from the mean, and we're only looking at 1/2 of that. So this is what I'm expecting. I'm expecting it to be about 0.15%. Let's find out. Normal distribution. Mean is 60%. Standard error, 0.0098, right? Was that what it was? 0.0098. What's the probability that we're at least 57% that we're agreeing here? Probability that of at least 57%. Oh, yeah. Oh, oops, I got the numbers wrong. 99.89% about. 99 point, I already forgot. 99.89%. All right, so our estimate, this estimate is actually 99.85. So yeah, pretty good estimate, right? 99.85% is our estimate from the empirical rule. So yeah, so it's almost guaranteed, right? Not quite guaranteed, but it's almost guaranteed that in this sample, at least 57% are going to agree with this thing that originally 60% of everyone thinks. So sample size is big enough that the variability is really low. That standard error, the standard deviation of the sampling distribution of proportions, there's so many words, so many definitions and math words in this unit. All right, this is pretty small deviation. All right, and that's what we got. One more video for extra practice if you want it. Otherwise, let me know if you have any questions.